All right. So this is the third and last meeting of the mini course.
Yeah, I just need to see the slides. It's
Okay.
Because with the spectators there, I was blocking all the time.
Oh, yeah.
It's fine.
You're fine. Okay. So that's the last meeting. It's gonna be about further perspectives. So the things that I'm currently working on. So everything I said last time was well, it's written properly. It's gonna be hopefully published soon, and it's to be found in my thesis. What I'm gonna talk about today is more conjectural, and not all the details have been checked. There may be some mistakes, so it's work in progress, but it's very exciting. So I wanted to share. And it's probably gonna be shorter. Let's see. So the plan for today is I will begin with different ways of generalizing the framework as presented last time. The main notion is a different perspective on the framing procedure, which turns out to be very powerful. I want to mention something that I'm far from understanding fully, which is a way in which I think some sort of background gravitational field can be incorporated into the framework. And then I will also argue that this whole game should extend to more general than quantum theories, to the GPT setup that we discussed. So that's the first part. And then I also want to mention categorical ways of thinking about the structures that we encounter. So I will define a category of reference frames and provide a functorial perspective on the yen. Do you guys know a little bit about category theory? Do you know what's a functor and the category?
Yeah, I should remember last time, we had this diagram, this commuting diagram.
Uh-huh.
I was wondering if there's anything that you can do categorically, because it looked like a very categorical statement with commuting diagrams. But I guess we'll talk about something like this with this factorial.
It's something I actually did. So I'm going to talk about frame changes in this categorical picture. Although something like an external frame change appears very naturally, so we can discuss this. Yeah. There is a beautiful structure, I think, here, and it can be grasped using category theory. And then based on this, I want to propose a definition of a relational process theory. So how this structure can be externalized, abstracted away to just categories. Okay, then let me begin. Consider the following thing. We have it's just quantum case now. So we have a POVM with values in the effect space and a function. So we haven't seen these functions yet. So let's say I have a function defined on the sample space of my frame observable, and it has to have the property that all such functions, so now it takes an element of the sigma space and evaluates the trace of the image of the F map on an arbitrary state, and this kind of function for any state should be integrable as a function on sigma. Yeah, I mean, it's maybe abstract, but this is the requirement that we need to the function has to satisfy in order to define this thing. So now it's just a bunch of symbols. I never told you how this yen is defined and how these integrals work, and now I'm gonna tell you how I think they should be thought of, which is different than how they were defined so far, and more general, and I think just better. So this symbol, what is this? This is supposed to be an effect on the composite system, and it is supposed to be, it is supposed to be framed. And so the way I define this is using this duality that we know between trace class operators and states. And effects and bounded operators. So what I'm gonna do is I'm gonna say what this thing is doing as a linear map on states. So what it does, okay, if I take a product state, and product states are dense in the full state space, what I should get back is a number between 0 and 1 defined by this integral. So this is the measure, the probability measure defined by the POVM on the given state. So I apply this omega into the first slot, and then I evaluate the function, the image of the function on X, which is now an effect on the state of the system. So this thing is now, because I assumed exactly that these functions, they're going to be integrable, then this integral is well defined, and actually it's going to be between 0 and 1 if the value of f is in the effect space. So what's written here is how this operator should work on product states. But since the product states, they're dense, well, the product trace class operators are dense in the trace class operators on the tensor product. This is enough to define the operator by extending it linearly and requiring continuity. So I think this is pretty simple. I mean, the setup is maybe, I don't know, there is a lot of notions involved, but as a definition, it's not much involved, and it does exactly what we want. So it is equivalent, I believe, to the definition given previously, because this is what it does, the previous definition on the product states. So they have to agree. But I find it very useful to think about these integrals in this terms. Is this sort of clear, understandable, what's happening?
A little bit.
A little bit, okay, I can repeat.
Yeah, but this is 0 and 1, okay.
So I want to define, I have a POVM and I have a function, and I want to put them together to define an effect on the composite system. A function has values in the effect space of the system, and the POVM is a POVM on the frame. And I put them together. I name this operator with this integral formula, and I say what it does to product states. And then I extend this procedure by linearity and continuity to define an effect on the full state space.
Yeah, it's not completely clear. You use the bottom thing, the last line, to define the integral in the middle.
Yes.
How you do that?
So an effect is an affine functional. So it has to take states to numbers between 0 and 1. So this is what it does.
Oh, the middle thing, this is supposed to be an effect, okay. Okay, so the thing with this is like a function. It's basically the function below there, is that it? Like,
what function?
Like this is a function, right? Like this is essentially a function, which is basically an integral, right?
No, so the whole thing, the integral formula, this is an effect, it's an operator.
Yeah, but like an effect is in the end a function, right?
A type of function. Well, yes, a functional.
Yeah.
A linear.
And now you're giving the definition here, right? Like
yes.
Okay.
Like what it does.
Okay, I get it now. Yeah.
Okay, cool.
Yeah, I was thinking like this was supposed to be like somehow the explicit form of this integral, but now it makes sense. Yeah.
Okay. Yeah, sorry. Okay. So, well, I think this works. If it doesn't, then then I will need to fix this. But I'm pretty convinced this can be made properly, rigorously, mathematics, so that I can speak about this integrals in this form. And then, if that's correct, then very interesting things happen. So, first, theorem that I want to prove, I believe it's true, is that whenever I have a framed operator, if you remember what the framing was, is that you can get there by just having the effects of the chosen POVM on the frame. Then there is always a function that corresponds to it. So for example, if you take this function to be constant on a subset and 0 elsewhere, then you get this basic framed effects that are just like the E of some subset, and then whatever you want, the operator on which f is constant on the system side. And by composing these things, this is how you get to the usual definition, the definition I gave last time, by just taking combinations of such simple functions, so to say. So this is why I believe this is true. Definitely the operators that I just described, they are framed, and I think the correspondence is actually a bijection. Okay, then with this definition, it's quite straightforward to prove that the only invariant observables that are framed, so these were the two conditions that we asked for, when the frame is localizable, the only ones, they are the relative one. So I was arguing that we have this relativization procedure that generates this invariant and framed observables, but now with this definition I think I can prove that if the frame is localizable, not in general, but if the frame is localizable, then I actually get to all the invariant and framed observables by taking the relativization procedure. So this is in a way justifying the whole yen construction, which normally just comes out of nowhere. And here this, well, if that's correct, then it says that this is the only way, the frame is localizable, is the only way to get into the physical stuff. And then another thing is that if I have a localizable frame that's not principal, so it's not defined on the group, but on some more general sample space. You remember that N was defined only for the principal frames. And I want to do the framing with respect to such a frame. So I have this sort of, if the first point is true, then I have these functions. And if I want this framed operator to be also invariant, then it has to be of this form. So now sigma is a section, so it's a map from the sample space to the group. So if sigma is just G, then it does nothing, and then it is just the yen as we know it. But in this general case, it provides a way to relativize operators with respect to this non-principal frame.
Thank you.
Does that make sense? You seem tired. I'm also tired, but I think it's good to finish with these things. So normally we have yen with the sigma is just identity on the group, and then this is yen. And it turns out that if I have a frame that's not principal, so it's sigma is just a space on which the group acts, but still I require the frame observable to be covariant. And then I can still generate invariant observables by this construction for any choice of sigma of such a map that is equivariant. So if you remember what's the equivariant, so if I act first, it's the same as I do nothing first and then I act on the output. If I have such a section, I can also generate invariant observables, and similarly, like I just justified the yen, all invariant framed observables will be of this form for some sigma. So this is quite powerful, I think, and it's so the sigma sections they just appear there. You can just, you just find them. Then, okay, they're here. Maybe they mean something. And so the next thing I want to only mention, because I'm far from understanding what's going on, but in a specific case, when the group is taken to be the Poincaré group and sigma to be a homogeneous space with the invariant subspace being the Lorentz group, so it's diffeomorphic to just a Minkowski affine space, so to say. These things, they get complicated, and I don't want to go into this because I don't fully understand it, but I want to share what I think is relevant. So consider the Poincaré group as G, and then sigma being the sample space on which the Poincaré group acts, and the Lorentz group being the invariant subgroup. Then sigma is homeomorphic to this quotient space, the big sigma, and the section now from sigma to the Poincaré group is going to look like this. Because the Poincaré is just translations and Lorentz, I take the connected component. So I mean, it just has to look like this, and if I also assume that it's equivariant, which is necessary for like doing the general Yen procedure, it's a Borel section and it's also smooth, then this section is analogous to a background gravitational field in which the frame would be embedded. And then so that's my understanding, so to say, what's happening. But what is, I believe I can prove, is that such a section specifies uniquely Lorentzian geometry on the sample space of the frame, which can be understood as as being exactly like analogous to the fact that when I move my frame somewhere else on sigma, then the geometry is going to change. And how it works roughly is that so this section is, and all these things are important. Like if you drop one condition, nothing works. So it needs to be equivariant and smooth and Borel. So if it's equivariant, then I can I can identify one point on sigma, which is the preimage of the identity element, such that sigma becomes diffeomorphic to the affine Minkowski space. And since it's smooth, it defines, I take the derivative, and now, so I guess that you can take, if you have a smooth map between manifolds, you can take the derivative, and then it goes from the tangent space to the tangent space at each point. So this procedure defines an affine connection that is torsion-free on the following bundle. So now, because sigma is, we've managed to identify it with the Minkowski affine space, and we have this sort of bundle, and this, again, sigma not only does the identification, but it also provides the connection on this bundle. And this is, mathematically speaking, this is the same thing as the tetrad the connection that is responsible for gravitational field in the tetrad formulation. One day I will understand it, maybe, and then I will let you know. But for now, this is just something that's very intriguing. Okay. So I like this definition of the framed observables because for many reasons. I mean, it makes the reasoning with these things much simpler, and it also generalizes to more general state spaces. So now, if I have an observable now on like any sort of system, so these are total convex state spaces, and I have effects on there that are affine functions, blah blah. So everything it just goes through. So I can pretty much repeat the definition. I need to assume this mu integrability of the functions, and then I can define this now as an effect, so an affine function on this, whatever those are, with the same formula. I mean, it's just you don't need to do anything. So the only notational difference that I don't have the trace now, but but the analog is just I evaluate the effect on the state. So you can stare at this for a minute if you want, but the point is that this perspective on the framing or on these integral operators just generalizes straightforwardly to other GPT theories. Just a comment, perhaps, but together with the following fact, so the same happens with when we talk about this restriction map. So we can always also write it down in this general case when you just have a state space because everything makes sense. So this is the same slide that I showed you last time for the quantum theory. The only difference is that you now have to think about effects as being affine functionals, and you can just do it. And since this all seem to work, so, as I said at the beginning, it's not that I checked all the details, but I checked many different things, and I didn't get stuck anywhere. So everything I checked is working, and therefore I believe that this formalism that I presented last week, on Tuesday, it generalizes to the GPT setting, because operational reference frame, the definition of a reference frame can be made because it's just an observable. Framing can be done, as I just argued. Localizable frames, they're also easily defined. You just you repeat the definitions, because the observables, they give you back probability distributions, and okay, if they can give you back localizable, highly localized probability distributions, the localizable frames. Okay, this general relativization, what I mean is this Yen construction with sigmas, with the sections, of course, the restriction maps, operational state spaces. So this I talked last time, that you can take the quotient in this general Banach space setup. So in particular, you can also speak about relative states, and that's all we used. For me, this is really amazing. I mean, if we can make it work, it's gonna be great one day. So yeah, so I think this setup can be lifted to totally convex state spaces. What you need to take sure is that you have the group representation on them, which no one knows how these representations look like, but you can just assume you have one, and then you can fly with this. And you need a notion of a tensor product. Also, I didn't talk about this. So obviously this, it's maybe not obvious, but there's ambiguity in the choice of the tensor product in GPTs in general. But the constructions that I showed you, they don't depend on this, because whatever definition you choose, it's always the case. They only differ in the way the resulting space is completed to a Banach space. But always it's the case that this product states, they are dense. And then you take the completion with whatever norm you want, which you can always do because you have this map defined just by as an affine function on the states. So I think, maybe I'm wrong because it's too simple, but I haven't been able to identify holes in this. I think it just seems to work, very surprisingly. All right, any questions here? That's also why I insist on speaking about this formalism as opposed to other formalism to quantum reference frames as being operational, because you can the notions that we use there, they have nothing to do in particular with quantum theory. They're just about GPTs, basically speaking. All right, then some categories. First thing I think is reasonable is to include this section to the definition of a frame. So a frame, unless it's just principal, it comes with a section. And then you can use this, if you do relativization with respect to this frame, you use the section that's provided.
So I should think of this section as essentially being the background space-time from what is it earlier? Or
That's one of the
Yes.
possibilities, but this only makes sense in the specific case of the Poincaré group. And but you can take any group you want and model whatever you want.
Okay, so in general scenarios, what should I think of it? Should it be some general space-time that might not even be physical, or?
It doesn't have to be space-time here. So we can take G to be like the real line.
Mm-hmm.
And say you're interested in maybe real line is not the best. But well, the plane like R2, and then your frame. Let's say it has it's a homogeneous space. So your frame cannot. Well, let's say sigma is not G, it's not R2, but it's R1 because the other R is not the action. Yeah. Sorry, I'm just tired. So the action is such that it leaves the other R, the other direction invariant, and then I mean you can also consider a section, and then it's going to be a function from R to R, basically speaking. I mean I don't think it's necessary to have this picture in mind, but I think it does make sense. But maybe you were asking, so
Yeah, I was just wondering what else should it be like if it's like. What is the physical interpretation of it?
Okay, so for me, I would say that G should be the Poincaré group,
Mm-hmm.
but then you can take whatever a homogeneous space you want. So you can, it can be the invariant subgroup can be trivial. Then you just have a frame on the Poincaré group, but it can be the Lorentz group, but it can be well, like whatever. So what's left can be just like one direction or two directions or just some combination or yes. Because I think, well, conceptually speaking, this G, the group that's underlying the whole thing is the represents, basically speaking, what can be done with physical systems.
Mm-hmm.
They can be moved, they can be pushed, they can be boosted, they can be well, you can decide when you measure time or not. So that would be my interpretation. But the framework just maths, and you can take any locally compact group. Okay, so since this section is equivariant and Borel, it gives rise to an equivariant map between Boolean algebras. That's just definition of being Borel, and therefore this general in this general sense, a quantum reference frame can be seen as a covariant. So before it was just a covariant observable, but now it's so when you compose these things, you get in the quantum case you get a covariant POVM that is defined on the group always, but it factors through the sigma space, the sample space of the POVM, well, of ER, but together they give another POVM. So I would like to treat this whole thing as a frame. So well, which is the same as I said before. It's just the old POVM plus a Borel section that's equivariant. But it is useful to think about it in these terms, so that it's a map that factorizes. Because then there is a very reasonable notion of a category of this sort of general reference frames. So now R and sigma, okay, this should be a small sigma, sorry. So R is just the frame that was before, so the representation, the Hilbert space, the covariant POVM, and then sigma is the section. So if I want to have a morphism between one frame to another, I would say it is a map, a pair of maps. And one is a channel between the quantum systems, and I require it to be equivariant. And the other map is an equivariant Borel map between sample spaces. So this is like the obvious thing you could think of, pretty much, just given the things. So yeah, is it clear what's happening? And then if you have these two things, I require that they will make some diagrams commute. So now this thing, well, this is the first POVM frame observable, and this is the map between algebras that Boolean algebras that the section provides, and so this is like the full information of the frame is given by this composition, and this is the other composition, and I require these maps that I take to make everything commute. So this is just a pretty diagram.
Okay.
But it really makes sense. So I will argue that this is not only just drawing nice pictures. It is powerful. It is a powerful definition. So this category I denoted just by this. So it has the category of frames, quantum reference frames. And now if I consider two more categories, so the category of representations of the group and channels, so these are the systems, because on all systems we had this unitary, strongly continuous representations. And then this is a bit more tricky. I want a category of operator spaces. We didn't talk about operator spaces, but they are Banach subspaces of algebras of operators. So for example, when we were generating a subspace of operators and closing it by spanning, for example, the framing definition, this is this was a Banach space that was a subspace of bounded operators on some Hilbert space. So this is a definition of an operator space, and you can have a representation on in the usual sense that restricts to a representation on the subspace. This can happen, and it actually happens for the framed operators. It does make sense, and it is needed already here to understand n as a functor, which is interesting in its own way, I think, because so now I'm gonna just say that n is a procedure that takes a frame and the system and produces the relative operators, the space of relative operators, which is considered to be the physical space of observables. And then if this makes any sense, then the requirements that we put on the physical observables to be invariant and framed, they force us to leave the usual Hilbert space setup and consider more general state spaces and spaces of operators that are connected to subspaces of operator spaces. So okay, this works like that. So n is a functor. I take the product of these two categories, and as a result, I get an element of the equivalent category, and it works like this. So if I take a frame, so R and sigma is the frame, and S the system, and I map it to the image of this generalized relativization map, and it's invariant. So this is how it works on objects, and on morphisms it's more involved, but so I'm saying the definition of the frame category is good because it works, it makes this thing a functor. So you can define, so a morphism mapped by n, so this should be a map from the relative operators with respect to the first frame to the relative operators on the second system with respect to the second frame, because well, we have now phi which goes from S to S prime, and like everything is moving. But you can, for example, if you keep S fixed, then you can view this as a frame change, as an external frame change. So you have a description with respect to the first frame, description with respect to the second frame, and you're able to map between one another. So this, well, you just do the obvious thing in a way. So so ER is now a map from the Boolean algebra to the effects on the first frame. So then you compose it with the channel that goes to the second frame, and you take the corresponding measure here, operator measure, and you apply phi to the effect on the system, and now this is not clear that it makes sense, because the result, it should be an operator relative to the second frame. And here you see there's still integration over sigma. But because we also have this phi here, we can use it to push forward this measure here and change variables. And because everything here was commuting, we will get the right. The result will indeed live in the correct space. And why is this map equivariant? Because the action on the because these are invariant subspaces, so the action is trivial. So every channel is going to be equivariant when all the actions are just trivial. So this is maybe a bit complicated, but I think it's nice. I like to think in these terms, and it provides another way of generalizing this whole story. So now consider we have a category, C, and a representation of a group in a category can be thought of as a functor. So now G, this bold G, is the category of the group that is thought of as just having one object, and arrows from this object to itself corresponding to group elements. So the composition is the group operation, and every arrow is invertible, and there is the identity arrow, which is the corresponding to the group identity. So it's a categorical perspective on a group, and when you consider a functor, then it will single out an object in C, and also morphisms from this object to itself, corresponding to the group operation. So if C is just like von Neumann algebras or operator algebras, then this sort of unitary representations, they provide exactly something like this. Okay, equivariant morphisms will be natural transformations. This is easily to check, it makes sense. So we define this category, and if we consider just all the arrows between objects, then this is the category of representation. So we can speak about all these things in any category, provided there are some factors from G to this category. And then we need another thing. So category of probability spaces. I didn't talk about this too much, so we agreed, I was arguing that it is reasonable to speak about these probability state spaces as an example of this total convex setup. But you can also show that this, so we got up to this duality that we had probability distributions being a total convex subset of the L1 space, and we have the L infinity as the dual, and these are exactly the von Neumann algebras. So you can think about the category of probability spaces as being commutative von Neumann algebras and channels between them, like normal positive unital maps. So there is a reasonable way to speak categorically about probability theory in this sense. And then I can require that this category of probability spaces is a subcategory of my category C. And why I need this? Because then I can think about frames internally, because a frame is just a channel from the objects of C, of representations of G on C, to probability spaces. These are like observables, and then on these probability spaces there is this. There are also spaces on which the group acts, and yeah, so we can. This is needed. Maybe I can show it again. Oh yeah. So basically, I replace this with an object in my category, and then I can speak about frames as being just arrows in my category. I don't need any other structure. And when this is done, I can define the category of frames, and maybe I have such a functor. If I'm able to define such a functor on my category, then I call it relativization on C. This is just lifting the the structure that we found to like as general setup as possible. And then if the category is monoidal, so it has a tensor product, and this functor, it has this property that okay, so this doesn't make, well, so what is this? The image of Yen is in here, is an object in the category, and if this is a sub-object, in some sense that we don't need to specify, of the of the product, of the tensor product of the two things that I started with, then I would like to call this structure G-relational process theory. The process theories, they're monoidal categories, and if they have G-relativization, that also is in ways compatible with the monoidal structure, which is the case that we've seen, then I think it's not a bad definition of a relational process theory. Yes, that's it. So these are all things that I'm working on, and it's going surprisingly fast, all these things. It is very exciting, and I think maybe, well, if half of this is true, then it's already great. Yeah. Any questions or thoughts?
So at this point, I have a very naive question. Actually, I'm curious to know your thoughts about the problems you're addressing with the quantum field development and how this framework actually can address those problems. Maybe we can talk about, because again, you're listing some problems about quantum field.
Yeah, I've said nothing about quantum field theory. Well, so for this whole thing to be useful, we would need to be able to model experiments, like scattering experiments.
Yeah.
And if we can do this in this relational way, then we don't need quantum field theory. That would be my take on the matter. Another thing I could say is that you can consider something like, so if you have a quantum field theory, which is like this net of algebras, let's say on Minkowski space, you can consider a POVM that's defined on this structure. So it's defined on the Minkowski space and gives you, it specifies an effect in each subalgebra. And since it's covariant, it's compatible with the quantum field theory structure. So we can speak about this sort of operational quantum fields. And they're just examples of quantum reference frames. So you can try to see what kind of observables you can define relationally in this sense. And so there's been some effort in the direction of specifying quantum measurement theory in quantum field theory. And I think this is highly related. So I haven't, that's why there's no slides on this, because I don't think I understood it well. Well, I understood nothing from what I was talking today, but yeah, I just need to get deeper into what's been done and look for these connections. Because so for now, my approach was just, so I learned about this structure from Leon like almost 2 years ago, about this relativization map, and then now I'm just going deeper and trying to uncover what is there. And sometimes something interesting happens, like, okay, I see I can generalize this to GPT. So, and then I see there is something that looks like a gravitational field. And then I see, okay, I can do this with categories, why not? And so I'm pretty sure, well, that's a very good question, and I cannot fully answer it. So these are my intuitions so far, but I really want to work on this. And yeah. Are we done?
I think so, yeah.
Yeah.
Questions?
Then thanks for coming. I will stop the recording.